Today we have a new topics, energy stores in an inductors. When an alternating current is connected in a circuit containing only inductors, there is energy stores in the form of uh, magnetic energy. So this energy containing in the inductors, after opposing the induced EMF, the work done by the source against the EMF induced in the circuits. So now let us start. So this is our AC circuits in which an alternating EMF is applied. Its value is E is equal to E naught sin omega t. So now this is our inductors. Inductance is L. This is a graph between current and times or theta, we can say omega t. So here it is a complete one cycles. In complete one cycles, it has 4 quarters. This is first quarter, second quarter, third quarter, and fourth quarters. We are going to discuss only one quarters. Suppose this is our one quarters, and one quarters where I have maximum value of the current at this times. So let us start to denote it. This is suppose I naught. This is the value of I naught. Maximum current in the circuit is I naught. In either directions, it is the positive first positive half, this is the second positive half. So, so when the current is rising, in this circuit, so magnetic fields, there is a magnetic field inside of this inductor. By the Lange's rules, so whenever there is a change of flux, it means that whenever either rising the magnetic field inside of this ones or decreasing the magnetic field inside of this inductors, there is induced EMF which opposes the change of magnetic field inside of this one. I mean that when there is a change of flux, magnetic flux is equal to B dot A. So its value is VA cos theta. Here cos theta has the value. Cos theta, omega is equal to theta divided by T. From here, its value become BA cos omega T. Omega is the angular frequency. So this is our magnetic flux. We represent generally phi B. So here when B is increasing, B magnetic field inside of this was when the current is rising from 0 to maximum, during this magnetic field inside of the conductor increasing, so flux is also increasing. By the Lange's rules, the inductor opposing the rising of the current during these periods, an induced EMF is produced in these inductors which opposing the rising of this current. So let us start. Suppose at the time of dt, the work done against this induced EMF is equal to dw is equal to P into dt. From the formula of the power has the value work done divided by time. Now power has another values also, EMF multiplied I into dt. So since the induced EMF opposing the rise of current, so we have to represent minus I before that. So this is the small work done in the time interval dt. Also an EMF induced in the time of t is E is equal to minus L di upon dt. So here this di upon dt is rise of the current in these circuits. So this induced EMF always opposing the rising of the current, also decrease of the current. So let us start. So what will be the work done if the current is rising from 0 to I naught, so that work done later stores in the form of magnetic energy inside of this inductor. So if I put the value of EMF induced E, which is minus L di upon dt in the equation number first. This small work done in the time of dt becomes minus L di upon dt into dt. After simplification, it comes out L di upon dt and into dt. So if I integrate these ones with respect to the time, means we got the work done dw and also L di dt in the integrations will cancel out. So it is the value of L. I would be there also minus L and I should be there. If I place the value of I here, I dt, and it has a value Li dt. So now we have to find the total work done from this point to this point when the current become maximum. So lower limit of the current is 0 and upper limit will be I naught. So we know that from the integrations, the formula of the integration is x raised to the power n dx is equal to x raised to the power n plus 1 upon n plus 1. This is the formula I am using here. Here L is the constant taken outside, and our variable is I has the power 1, so 1 plus 1 divided by 1 plus 1, and this is definite integrations, lower limit 0, upper limit I naught. After simplifications, L upon 2 taken out, and inside of this ones it has the value I square. Lower limit of the current is 0, upper limit I naught. First put the value of upper limit, then lower limit. If I put the upper limit, it has the value I naught square minus 0. Upper limit, place I naught in place of I. Upper limit I naught square minus 0. After simplification, it becomes L I naught square divided by 2. So this is the work done. This is the work done during the rise of the current, when the current rises from 0 to I naught. So I have did this work. This work is done by this source, alternating source. Again, this induced EMF. The induced EMF generated in this coil. So this work does by conservation energy. It will not goes to waste. So it will be stored as a potential energy. This work done is stored as potential energy. In the magnetic fields of inductor. We can say that this will be the magnetic potential energy. Because this energy is stored finally in the magnetic field of this inductor. So from 0 to maximum, this much of energy is stored in the magnetic fields. Yes. Now, similarly, second quarter, if I was in full cycle of this oscillation of alternating current, in first quarters energy stored in the inductors. Second quarters, the energy which is stored in the magnetic field of the inductors returned back to the source, and again the direction change of the current in second half cycle. This is second half cycle, and this is our third quarter. In third quarters, energy again given by this source to the inductors in the form of the potential energy, and fourth quarter, this energy which is stored earlier in the magnetic field of the inductor returned back to the source. So in a complete cycle, if I consider in a complete cycle, the net work done will be 0. There is no work done in the complete cycle, but in a quarter cycle there would be some net work done which has the value of this one.